let's start this now. Couple of administrative notes before we get started. Oops, this isn't, well, it looks the same. In the assignments, I posted a couple of new assignments that hopefully you've noticed. Assignment 12's been up for a while, but assignment 13 and bonus assignment 2, in case you're interested. I just posted over the weekend, and so assignment 13 is on the chi-squared goodness of fit test that we did last day. We only had time to do one example, so it might be nice to kind of go through that example that's in the slides just to solidify some concepts, but also the assignment. And then there's a bonus assignment on the next level, which is if you have two categorical variables, right, that you want to test if they're independent of each other. Okay, and so it's a bonus assignment, so it'll be dropped if you decide not to do it, but that just means if you do it and it's better than a previous assignment grade, if you miss one, for example, then it'll be replaced. So it'll just drop your lowest assignment grade. And so far we've had 2 bonus assignments. So that's just how they're going to work. I do want to show you, even if you don't do it, there's a link to a video. It's that Z statistics guy. He does a really great job. And so if there are other concepts that you're maybe struggling with, he has a really nice, clear way of explaining things. And so even if you don't do the bonus assignment, it might be worth a watch. And I don't know how he does it so quickly. He just covers a lot of ground, and I'm flabbergasted. So for the labs, gets a little wonky because, yeah, question?
Sorry, I didn't interrupt you.
No, that's okay.
Where's that video on sample size?
Huh. Where is it? Where is it? How about I make a note to myself? I'll do it in red. Self-punishing. No, just so I notice it. Emily, N calculation? Video? Do this. That's for me. I'll hopefully remember to delete that before I post the notes. But for us, so I'll figure out where that is. I know where it would be, but I might not have put it out to you. So this week I posted lab 9, which is inference for means. And if you tried to do it yesterday, that'd be hard because we're just introducing it today. And then there are no labs the following 2 weeks. So the next 2 weeks, there are no labs scheduled. Let me just. It's kind of wonky because there are Monday labs and there are Friday labs. So as a rule, if there's a holiday and there are labs on those days, we cancel the labs throughout the week. Otherwise, it gets weird. But now we had 2 in a row. Sorry, kind of making a mess. But I'll make lab 10 available to you. And wow, isn't that nice? So that you could have it done. And it's an introduction to linear regression. And I encourage you to do it before we introduce linear regression, because it just gives a nice outline of what we're going to be doing at the very end of the term. So for you guys, no labs the next 2 weeks. Gives you time to get caught up a little bit, right? But lab 10 will be available. But then there will be labs in the last week of classes. Usually that's not the case because That's just not how it's done, but we had to squeeze one in at some point, and so I'll if you're in one of my lab sections, I'll be there for the last week of classes if you need help with lab 10. Okie dokie, artichokey. Here we go. Today, we're starting chapter 7, which is inference for numerical data. Okay. And so inference for numerical data. Bless you. So far, we've only talked about categorical data, inference for categorical data, right? 1 sample proportions, 2 sample proportions, 3 or more proportions that you want to compare. And then if you want to do the bonus, right, then you have 2 categorical variables with different levels of proportions or different categories. And so now for numerical data, and because it's the name of the section, maybe or the chapter even, should write it so you can kind of read it. Numerical data. If we have numerical data, thinking back to kind of the very beginning of the course, numerical data, usually we're interested in the mean, right? And so now we're going to be analyzing the mean. In fact, inference is confidence intervals and hypothesis testing. And that's how we analyze the mean. This is the most common type of analysis that we do, but we start with proportions because they're equally important. But we start with proportions because they use a Z for their test statistic, and Z is stable, right? Whereas now in this chapter 7.1, we're going to be talking about 1 sample mean with the t distribution. We've seen that we've worked with the t table already. We've ignored that middle chunk. Well, today we can't ignore it anymore, but the t distribution is a little bit trickier just because it depends on the sample size. The shape depends on the sample size, very similar to how the chi-squared behaves, right? Depends on how many categories you have, that determines the shape. And so all these concepts we've seen before, but now we're going to work with the t distribution. And if you're talking to anyone about statistics, anyone who's taken a statistics course or does even a little bit of statistics on the side, they'll say, oh, like you just run a t-test. Just do a t-test, you'll be fine, kind of thing. And so that's what we're introducing today. Okay. So we're going to do t-tests is what we're introducing. T is the test statistic, and a test means it's a hypothesis test. Okay. All right. So far, we have only talked about proportions, right? Proportion type questions. And then we had to determine, is it 1 sample proportion, 2 sample proportions, 3 or more sample proportions, right? And so now when we're introducing means as another type of question, right? That's going to be your first fork in the road. Do I have a proportion type of question, or do I have a means type of question? Okay. And so I stole this from a different textbook just to illustrate the 2 examples of how the questions are going to be worded. Ultimately, your job is to answer questions on a test and on the final exam. So you have to be able to identify what type of question you have. Okay. And it sounds silly for me to say it, but the word proportion will be in the question if it's a proportion question. And the word mean or average will be in the question if it's a means or an average type of question, right? So a means type of question. And so that sounds easy enough when I say it, but if you're like me, when I took my first stats course, it all kind of made sense when I was sitting there, you know, they're saying stuff and okay, yeah, sure. My prof swore a lot more than I did though, or do, just in general, I think. But same idea. So I'm nodding along, I'm getting it. And then I walk out and I go to do the problems. Man, that's not as easy as it felt in class. And that's normal, right? It just takes time to practice these things. So if we read this, this blurb, members of a political party in Texas are considering giving their support to a particular candidate for election to the US Senate, and party leaders want to estimate the proportion, okay, of registered voters in the state that favor the candidate. A sample of 400 registered voters in Texas is selected, 160 of those voters indicate a preference for the candidate. Okay, I'm going to skip the last section. Here, I have a sample of size 400, and I'm told that the number of successes, right, the voters who indicate their preference for the candidate, in this case is a success, right, X is 160. That's all the information that we need for a proportion question. How about a means type of question, right? And so for means type of questions, we're going to need a little bit more information, but not a whole lot. So a means type of question, and just thinking about any sort of business analysis that you would want to do, usually it's about the means, right? Average revenue, average sales, average customers, average whatever, right? And so it's not helpful. Just the average is what we're interested in. And so usually we are dealing with a means type of question, but sometimes you have categories. So a tire manufacturer is considering production of a new tire designed to provide an increase in lifetime mileage over the firm's current line of tires. To estimate the mean, okay, I'll highlight that. Useful life of the new tires, the manufacturer produced a sample of 120 tires for testing. And the test results provided a sample mean. Okay, and so that's another one that I'm going to highlight, of 36,500 miles. And so now I have some more information or some new information. I still have a sample size, so that's great. We'll still have a sample size, of course. And do you remember that the sample mean is denoted by X bar? That's been a long time, right? So anything with a bar over it is a mean, right? And so X bar is typically how we denote the sample mean. You might see some textbooks that use Y bar, oh, crazy. 36,500. Yeah. And so that's, like I said, kind of your first fork in the road for deciding what to do with this problem, how to solve these problems, okay? From here, we would make confidence intervals, do hypothesis testing, and we're also going to follow the same format that we did for proportions, right? We're going to start today with one sample mean, which I can't do much with except compare that sample mean to some number, just like one sample proportions, right? And then kind of fun in the mean scenario, if we have two samples, they can be paired samples or they can be independent samples. And so that gets a day each for us. We'll talk about those two scenarios. And then if we have time, which I don't think we will, which sounds like a bonus assignment to me, 3 or more means, right? And ANOVA. And so same layout as we had for proportions, just now we're doing it for means. Okay. All right. This slide just says what I just said, so I'm gonna skip it. These slides, I flip-flop back and forth on how I deliver my course material. And so these slides are kind of old, and then I tried to tweak them and I don't know, I wasn't paying attention, I guess. But now, I'll copy this first, but now, look at all this. If you've got the formula sheet, or if you're missing a formula sheet, you can grab one up front here. But look at what we've done. This is crazy, right? First page, we did that, 1 sample proportion, 2 sample proportions, looks bad, but it's not, right? Chi-squared goodness of fit, right? That's 3 or more proportions. This, I want you to make a note that the chi-square test for independence is the optional, it's the bonus assignment. So it's not going to be on the test, of course, that'd be crazy. And then I snuck in this table of critical values. Otherwise, there'd be another handout for me to lug back and forth to class. And we don't need that. Save the trees. And now 1 sample mean. Okay. Knowing the lay of the land here, I suspect it'd be really, really mean. But I suspect I could kind of push you in the deep end and make you do a confidence interval and maybe probably even a hypothesis test, even with this. That sounds scary. We're not going to do that, right? We're going to do it together. But I think I could do it. I'm confident in your abilities at this point, even though it's brand new. Okay. And so that's got to feel really good for you. Well, it feels great for me. I'm so confident in your abilities. Just as before, the central limit theorem applies. Now, what that means is that if some conditions are met, and we'll talk about those conditions, then we can assume that it follows a normal distribution, which is awesome, right? Because then we can find probabilities, bada boom, bada bing, and we're off to the races. This, just as before, this chunk, right, is just theoretical. So you're never going to use that. That's not going to be part of your solutions ever. Okay, you're using it implicitly, but sometimes I see people trying to use it to solve a problem, and it's not going to get you anywhere. And so we use it implicitly, but not explicitly. What's it saying though? X bar. Remember that tricky lab that I made you do where you generated 100 sample proportions? What if I did the same thing, but I made you do 100 sample means? You would find that it would follow a normal distribution centered on the population mean, mu, with a standard deviation of the population standard deviation divided by root n. This becomes the standard error, of course. Of course, she says, standard error of X bar. Okay. We use that for our confidence interval and for our hypothesis test. Okay. And so let's see here. Our inference, right? Anything that we're trying to learn about has to be from the population, right? So let's just remind ourselves that mu is the population mean, right? Just like I was trying to learn about the population proportion, I'm trying to learn about the population mean now, right? And so here, mu is the population mean. I don't know what it is, right? But that's okay, because what do I have? I have X bar, my point estimate, right? And so this is the sample mean, which is my point estimate, my best guess at what mu might be. dun dun, T star n minus 1, subscript n minus 1. This is really taking the place of that Z star, right? And so thinking about our T table, we've seen it there before. And if you look at the column on the left, let me go to the table and show you. Oops. Here, we've been ignoring all these, but what are they? They're degrees of freedom. We've seen degrees of freedom for the chi-squared, right? And so we're going to have the same type of scenario here where the sample size is what dictates your degrees of freedom and also the shape of the distribution. But besides that, these values here are now T's, right? We were just focusing on Z down here, but the behavior in the table is the same, just now we have T's, and that's really the only change. So knowing that, and if I told you that the degrees of freedom is n minus 1, which is also down here, let's see if I can sneak this around somewhere. This subscript n minus 1, you can skip it if you want. It's just telling you how many degrees of freedom you have. So let's say, just as a quick example, just to show you that you actually know how to do this stuff. I want to make a 95% confidence interval, and I have a sample size 21. How many degrees of freedom do I have? I have 21 minus 1, immediately 20. It's almost like I doctored it. I did. So then I'm saying that, okay, I found my degrees of freedom, and I said it's going to be 20 degrees of freedom. Just like before when we were stuck on the Z star line, now I can ignore all the other degrees of freedom. Why? Because my sample size doesn't change, right? It's just 21, now I'm stuck here, right? And so now if I want to make, let's say, just as an example, a 95% confidence interval, then now my T star would be 2.086, close to 2, right? Which we already have a good understanding of. So things don't change that much, right? The only thing is for Z, it was 1.96. For a T, we move out just a little bit more because there's more uncertainty, but not that much, right? 2.086 isn't that far from 1.96. So they're all in the realm of 2, right, for a 95% confidence interval. And so even though this looks bad, the T star n minus 1 is the subscript. Oops, that looks like 9. N minus 1 is the critical value, right? How many standard errors do you need to move out to capture the central 95% or 99 or whatever? So this is your critical value. Fine. It's been a while. S is the sample standard deviation, right? S is the sample standard deviation. Just chipping away at all these components. And then of course, N is still our sample size. That's never going to change. Okay, and so N is the sample size. Okay, then I'll also make a note that S over root N is the standard error of X bar. And it stems from here where, okay, technically the standard deviation of X bar, would be the sample standard deviation divided by root n. You can see how that's messy, right? There's a lot of sample standard deviations in there. And so that's not going to work. And that's why we have this new terminology calling it the standard error, which wasn't obvious before in the proportion case. But here you can tell it gets boggy. And so sigma over root n is the standard error of X bar. What's really nice, right? If we think back to proportions, then the standard error for the confidence interval was slightly different from the standard error of the hypothesis test, right? Or the test statistic. Now we're on easy street. They're the same, right? In fact, my best guess at what the population standard deviation is S, right? And so S over root n is my best guess at what the standard error is. And so that's really nice. We're going to use that here in our confidence interval, but also here in our hypothesis test, right? But then just skipping the null hypothesis for just a brief moment, if I talk about the test statistic, T, our third test statistic, can you believe it? Z, chi squared, right? And then T, aha, look at us go. Still takes the point estimate. How far is my point estimate from some hypothesized mean, right? Okay, seen that before. And then in terms of the standard error, in terms of the spread of this thing being X bar, of course. Okay, so for one sample problems, I find that they're almost hardest because you have to figure out what value do I want to compare my one sample to. As soon as you have two samples, obviously you want to compare them to each other. So then there's nothing left to do, right? But for one sample, there's going to be a value in the question that you want to compare your sample mean to, right? And so mu naught, just the same as P naught was, mu naught is the mean you want to compare your sample mean to. You want to compare your sample mean to. Okay. So then if we go back to your null hypothesis, right, it has to be about the parameter, it has to be about the population mean, mu, and how it compares to some number, right? Mu naught is a placeholder for a number, just like P naught was a placeholder for a number. Okay, now I think the next few slides are all talking about the conditions. Now, what I want to do is just give you a brief shorthand of the conditions, and then we'll kind of skip some of these slides. You can have them just for reference. But at its heart, the conditions for the central limit theorem to apply are these. As long as the observations are independent, how can I make sure they're independent? Well, the same way that we have been doing. If I've randomly sampled, I can assume that they're independent, right? So here, random sampling. And then here's the new thing. So, and the population distribution is not extremely skewed. Then a large sample, so a sample size of 30 or more is what we're going to use, is going to ensure that the sampling distribution of the mean is nearly normal and that we can use S over root n as a reliable estimate. Okay, I'm going to just shorthand that a little bit even more. So for us, the conditions and I'll say for one sample mean, right? You've determined, read the question, figured out it's a one sample means type of question. So for one sample mean, regardless of if it's a hypothesis test or a confidence interval, that's really nice, right? The proportions really put us through the ringer because the conditions are different depending on what you're going to do. Now they're the same and really quite simple in comparison. So we still have an independence condition. And how we ensure that it's met is if we've randomly sampled, or what? You have to assume that you randomly sampled. Even if it doesn't say, we assume that these things are independent, and that's good enough. So random sampling ensures independence. Oops. We're used to that one, right? Randomly sampling, okay, then I can assume independence. The normality condition, right, can go one of two ways. So if n is greater than or equal to 30, we can assume normality. That's really nice, right? If we reach a large enough sample, then even if we're drawing from a skewed distribution, we can assume normality because the means will follow a normal distribution. As long as you remember the two different options here, you're okay. You don't have to worry about the intricacies of the central limit theorem. But if the sample size is large enough, so n greater than or equal to 30 is what we're going to use, we may assume normality. That's nice. What if n is less than 30? We can check that the sample is approximately normal by making a histogram. That's one of the things. And if it is, then we can assume normality, right? And so what we can do is usually we just argue that it would follow a normal distribution. And so if n is less than 30, we should check, or we should make a histogram of the data to ensure it's approximately normal. Now I kind of trained you to say, well, even if it looks a little bit skewed, right? You kind of got to squint at it, right? You can't be too picky because we have to argue that the normality condition is met, right? So you would say, well, it's a small sample size, but I suspect that if we collected a larger sample, it would follow a normal distribution, right? That's one of the ways we can get around that. So if n is less than 30, we should make a histogram of the data and make sure the distribution is approximately normal. For us, that's one of these two are going to be met, but just if you have a small sample size and it is extremely skewed, then there are other methods that we're not going to talk about in this course, but you could look them up. They exist. Okay. Cute little conditions, right? Not those monsters we're used to seeing, right? And so, of course, I have all these slides which kind of talk you through blah, 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 but we did talk about the assumptions already. Even here, it's a long-winded version of what I just said. This, the independence condition, the second independence condition is very similar to the n less than 10% of the population condition. So the population must be much larger than the sample, say at least 20 times as large. I'll just write that this is optional And I'm not expecting you to do it. In fact, I don't check that one because it's always satisfied. Okay. When these conditions are satisfied, then the sampling distribution for X bar is roughly normal. Now, what we said was, okay, fine, I have X bar, so my sample mean, but I don't know sigma. So then I have to use the sample standard deviation. So now I'm using two things from my sample, but I also understand that if I were to collect a brand new sample, then there would be variability in my X bars, but also my S's, right? And so each new sample would have variability in the X bar and the S. And so you don't need to worry about that, but it becomes kind of like when you're, what is it, patting your head and rubbing your stomach at the same time. X bar and S are kind of moving alongside each other. Yeah, wow. I don't know if I can do it under pressure. No, I can't. Just rubbing my head. Anyways, right? And so that's why we can't use the Z distribution anymore, because we have movement in both X bar and S at the same time. But that's where we can use the T distribution. So hard to see. So here, maybe this is how I should practice my writing. I can't follow the, this looks worse than what I usually write. The T distribution. What a mess. The T distribution is very similar to the Z distribution or the normal distribution because it's still centered at 0. Okay, that's nice, which means that we have symmetry around 0, right? We can have negative T's and positive T's. It is still bell-shaped. The only difference is that the tails are thicker than the normal distributions. If you've got kind of thicker tails, and there's an image here. Okay, so the dotted line is the normal distribution, so Z. And the blue line is a generic T distribution. Okay, what's going to happen is the T distribution, right, looks the same, right? It's centered on 0 here. Anything beyond 2-ish is considered extreme, right? And so the area under the curve is still a probability. All these same concepts apply, but notice here that the tails are thicker, right? There's more room in the tail than the normal distribution. What does more area under the curve mean? It means what does more area under the curve mean? Yeah, okay. I don't know why I stumbled there. It means the probability is higher, right? It increases the probability. So the probability of seeing a T of 3 is higher than the probability of seeing a Z of 3, right? Same thing for 2, right? And so this area in the tail, right? Thicker tails mean a higher probability. Just allows for more variability, right? And it's because the X bar and the S's are changing simultaneously, or at least in theory. Okay, so the tails are thicker than the normal models. So observations are more likely to fall beyond 2 standard deviations from the mean than under. So we used to have 2 as our cutoff, and it's still a good kind of mental cutoff, right? A T plus minus 2, probably going to reject H0 if you have a large enough sample size. Okay, and so if you have a large enough sample size, well, that means that it's going to hinge on the sample size, of course, and that's where the degrees of freedom come in. And so the t distribution has thicker tails for small sample sizes, and then as the sample size increases, then you get closer and closer to the z distribution. You can think of it as approaching the population. As you collect more and more of the population, right, things become more stable. And so I kind of do my arms like this. If you're online, I can't describe it. I'm making a normal distribution with my arms. And so if you have a small sample size, then it's going to be basically flat like this, right? Saying, I don't know what's going on. You didn't collect a big enough sample. And then as we increase our sample size, the tails are going to push down on the axes, right? And the peak gets more prominent. And so that's how the shape of the t distribution is going to change. And so how we communicate that shape is through the degrees of freedom, which we've already seen. And for one sample, it's just n minus 1. Okay? And it's a grayscale, which is nice, but also kind of hard to read. Let's remind ourselves that the degrees of freedom is n minus 1. It's easier to think about the degrees of freedom in terms of the sample size. And so here, if I have 1 degree of freedom, what's my sample size? Must be 2, right? And so would you ever analyze something with a sample size of 2? Probably not. So it's not really relevant. Even if you only have 2 degrees of freedom, then you have a sample size of 3, 6, even n equals 11. These are all small sample sizes, right? And then we have the normal distribution, which is z, where n is the population size. If you have the entire population, then there's no variation in your sigma, but there's also no variation in your mu. So why are you trying to figure out what it is by guessing? Makes no sense. So that won't happen, but it's nice to have kind of a top end point. Okay, and so looking at these distributions, in my mind, if I have a sample size of 2, right, then I would expect this thing to be just flat. In fact, it's not even that flat, right? The tails are the thickest, but still not unreasonable. There's still this kind of normal or bell-shaped curve, right? And even at a sample size 11, it's basically at the normal distribution. So it's basically at the Z already. So we don't need a huge sample size for this to happen, right? And so that's kind of cool. Yeah. Now we've already used the t-table, so I'll keep these here because it introduces it as if it's the first time, and maybe if you need a refresher on using the t-table, then I'll keep those there. But what I want to do is have some fun. Let's see here. Oops. How do I managed to get it before, but I guess I can't do it. Okay. So now we have our t-table, and I'll just grab a chunk of it, copy, and paste. And I'm not going to do the whole thing because it's quite large. Oh, but I will do there. Okay, so of course it keeps going. But here's, I still can't squeeze it on one page there, or one screen. Z table or T table, you have it in front of you, probably, maybe. And so we said, okay, my degrees of freedom is going to be n minus 1. Once we have that, right, that degrees of freedom line, let's say you have 30 degrees of freedom, just for as an example. Like we said, your sample size isn't going to change, right? You have 31 to get 30 degrees of freedom. And so that's not going to change. So now what do? You can ignore all this, right? Because they don't apply. That's the exact same thing that we were doing down here with our Z star line. We said, oh, don't worry about all that gibberish up above, right? You can just focus on the Z star line. And so the same rules apply and the same methods apply. It's just that now we have that additional step of needing the degrees of freedom, but after that, everything's the same. So let's say we already did an example. I'm going to let n be 31. So then my degrees of freedom is n minus 1, which is 31 minus 1, which is 30. Just as an example. These values are all t's, and just because t is also symmetric around 0, right? If you get a negative t, then you take the absolute value of it, and then you find it on this table, right? Behaves the same way that Z did. Let's say, without even doing a calculation yet, let t be 2.000. Find the p-value, find the one side, or let's find the two-sided p-value. You're going to take your t that, well, actually, let's throw a wrench in things. Let's make a negative just to really show off everything that we have, right? And so then we would say, in our description, we would say, using the t table with degrees of freedom equal to 30, we find that the absolute value of t equal to negative 2.000, oops, is between these two values. That's the same setup that we use for Zs, right? And so that's why I wanted you to use it, so that now it's not that hard to extend it to t's. So then I go along this line and I try to figure out where 2 would fall. 2 is between 1.697 and 2.042. And so here I have 1.697 and 2.042. Jot down what t's wrap around the t that you've calculated. So the two-sided p-value is also between two values, which I'm going to circle these values here. And just as before, right, I either have a one-sided p-value or a two-sided p-value, which is from the alternative hypothesis, right? And so now I have a two-sided p-value. So I go down here, and my two-sided p-value is somewhere between 0.05 and 0.1. Okay? So it's the same layout as what we have been doing. Just remembering to read these from right to left, or at least write them from right to left, right? Because as your t's are increasing, the area in the tail is decreasing. All right. What happens? What if your n is 57? Uh-oh. just as another example, let n be 57. Then your degrees of freedom would be n minus 1, which is 57 minus 1, which is 56. Okay. Up till 30, I can get the exact degrees of freedom in the table. Of course, software can always get you the exact degrees of freedom, but now I'm choosing, so I have 56 degrees of freedom, but I'm choosing between 50 and 60. Now here, you want to be really careful, because what does choosing 60 mean? Means that you are saying you had a sample of size 61, but you only had a sample of size 57, right? So you're claiming to have more reliable results than you actually do, right? And so what do you have to do? You would have to round down to 50 degrees of freedom. For some reason, it feels painful, right? But I could be rounding up. Well, it doesn't matter, right? Comparing at these values, is it going to make a huge difference? No. So we just round down to the nearest line. And so, but would use degrees of freedom equal to 50 in the table. So here I'll make a note. If the exact degrees of freedom is not listed in the table, we must round down to the nearest degrees of freedom. We must round down to the nearest degrees of freedom. Yeah. Good. Even if you have, let's say, 900 degrees of freedom, of course, you'd probably be using software at that point, because that's crazy. But 900 degrees of freedom, you're choosing between 100 and 1,000, and you're so close to 1,000, but you'd have to go down to 100, right? And so, but should be using software, but just because we're using the table, you have to know how to use it properly. Okay. This is the part of the course where everyone's got a pretty good handle on, okay, these p-values, they're important. I know that, right? Everyone's like, oh, okay, yeah, that's important. But what are they? It's okay. Question, comment, concern.
Are you ever going to make us calculate the exact p-value?
No. I do on the assignments, because then you can have software. The only reason I do that on the assignments is to show you that the exact one exists. Okay. And if you were working in real life, that's the p-value that you would use, obviously. But on the test, you just have the tables. So just the tables for the test. So we need to be able to use both. That's why the assignments do both. But no, not under pressure. No. So what is the p-value? Unfortunately, all I can do is just give you the definition again. That's all I can do, right? Until it sinks in, and eventually it will. So let's just kind of reiterate what it is. The p-value is the probability, right? It's a probability of seeing something as extreme or more extreme. And what that means is the probability is an area in the tails, right, under the curve, but as extreme or more extreme puts me in the tails, right? Of seeing something as extreme or more extreme than what I saw in my sample, assuming the null hypothesis is true, right? There's no easier way to break it down. And so here it's the probability of seeing something as extreme or more extreme than what we saw in our sample, assuming H naught is true. And for that reason, if the probability of seeing, now we're talking about means, a sample mean so far away from the hypothesized mean is very small, right? That's evidence against H naught, right? And so that's why if the p-value is small enough, then you have enough evidence to reject H naught. That stays the same. That's always going to be the case. Okay. So I know p-values. We ready for an example? How am I doing for time? I can't see that. All right, power up. Power down. I don't know. Here's an example. The level of dissolved oxygen, DO, in a stream or river is an important indicator of the water's ability to support aquatic life. So a researcher measures the dissolved oxygen level at 15 randomly chosen locations along a stream. Here are the results in milligrams per liter. So we've got 15 measurements, randomly selected locations. These are numerical, right? And so I can find the mean and the standard deviation of the sample. And so here I give you X bar is 4.77 and the sample standard deviation is 0.94. Okay. So I have two pieces of information, right? I have to have the mean and I have to have the standard deviation of the sample. So those are the two things that I need from the sample. Well, and the sample size, let's add that n is equal to 15. It's there, but now here's the problem. A dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. That would be a concern, obviously. Is there evidence that the aquatic life is at risk at the alpha equals 0.05 level? All right, we can do this. All right, let's see here. Going to be adding pages galore here. First thing I want to highlight is that, okay, I have the sample information, X bar and S and N, and what's the value I want to compare my sample mean to? I want to compare it to 5, right? Which means that mu naught must be 5. In fact, I'm concerned that it might be less than 5. Looking at the numbers, 4.77 is less than 5. We are going to determine if it's significantly less than 5, right? Is there concern? There's some wiggle room around 5, right? But depending on the spread, right, that's going to dictate if we're significantly less than 5. So from the question, we're ready, just like that. Step 1, steps are the same. State the hypotheses. From the formula sheet, we have the null hypothesis is that mu is equal to some mu naught. I'm going to replace that mu naught with 5 now, right? Because that's from the question. Just like when we had p naught was from the question. And so I'm going to replace this with 5. I have to assume that the mean is basically 5. 4.77 is basically 5 until I have proof otherwise. And the only thing that I'm concerned with or that seems to be a concern, is what? If mu is less than 5, so a level below 5. And that's going to be my alternative hypothesis. I'm only concerned about this one extreme. It seems from the question that any higher level is fine. The fish are they're all happy still. So we're only concerned if it's less than 5. And so this is a one-sided test, right? I like to make a note of that here. We don't use it until step 3, but it's nice to kind of have it somewhere so you can remind yourself. Okay. One-sided because I'm only caring about one extreme. Now let's just briefly check the conditions here. The locations were randomly sampled, so that's good. The independence condition, I'll say locations were randomly sampled. And I should say, therefore, we can assume independence, but I don't, and you don't have to either. The normality condition, that's the new one. If the sample size is large enough, bigger than 30, then we can assume normality no matter what, basically, for our purposes. Now, we have a sample size of 15, and so n equal to 15 is not larger than 30. So we assume that the distribution is approximately normal, right? Ideally, we would make a histogram and look at it and say, oh, it looks approximately normal to me. And so, but we're just checking the conditions or stating our assumptions. And that's my assumption, is not larger than 30. So we must assume the distribution is approximately normal. Fair enough? Not really, it's kind of weird. But therefore, the conditions for the central limit theorem are met, or apply, or something like that. Looks like meat, but it's not. Okay. Now we're ready for step 2. Our shiny new test statistic. Do the test, which is really calculate the test statistic. But that sounds boring. From your formula sheet, right? Let's see here. I'll just go grab it. From the formula sheet, this T is your test statistic, hence the term t-test, which is commonly used. And so T does the same thing as all our other test statistics. It takes our sample mean. How far is it from our hypothesized mean? Taking into account the spread of X bar, which now is S over root N. Okay. T, X bar was 4.77 and S was 0.94. So we have 4.77. How far is that from 5? If the spread is 0.94 divided by the square root of 15. Now, oops, nope. Let's see, I already did it. I have a screenshot somewhere. Maybe this one. Cancel. Oh, it's not doing anything. And unlike last time, I double checked it so I didn't have a typo in here. So T is roughly negative 0.948 to 3 decimal places. I'm using 3 decimal places because the T table has 3 decimal places. And so you have to keep at least 3, but you can keep more if you want. Okay, this tells me that 4.77 is 0.948 standard errors below 5. That's not very far by any standards, right? By Z or T or anything. And so in fact, a T has to move further out than a Z did in order to be considered significant. And so now, I'll give myself a page right away. Step 3 is find the p-value. In order to use the table, we need the degrees of freedom. And so I'm going to use the same blurb always now, and I'm just going to articulate all the things that I'm about to do. So using the T table with degrees of freedom equal to n minus 1. Now this is your way of safeguarding what all your marks, right? If you tell me that the degrees of freedom is n minus 3 for whatever reason, and then you followed through with that, then I'm not going to argue with that. That's wrong here, but if you follow through, then that's fine, right? And so here, you're just going to show me all the things that you're doing, which is 15 minus 1, which is 14. So you just do your calculation there. We find, I'm going to set it up just the same way that we set it up for Z's, right? Because it will be the same layout. The absolute value of T equal to negative 0.948 is going to be between 2 values. So the p-value, and I'm going to specify / remind myself if I have a one-sided or a two-sided p-value. I had a one-sided test, so I need a one-sided p-value. So I'll jot that down. And now I'm ready to go into the table, right? You can jot all this down and then just fill in the blanks with the table. I'm just going to take the parts that I need here. Copy. Of course, you'll have it in front of you, but it's just hard to flip back and forth. Close enough. So now I have 14 degrees of freedom. It's our first example, so it exists on the table. That's nice. I dropped the negative, right, by taking the absolute value. So 0.948 on this line is going to be, well, I don't get to go very far, do I? Somewhere between 0.868 and 1.076. That makes sense because we're not moving very far from 0, right? So we wouldn't move into the table very much. That would go in here. So then I'm going to write 0.868 and 1.076. This is another way, so I want to see it this way, because this is another way that you're gonna just show me what you did. If for some reason you make a little typo and you tell me it's between these two because you're in a hurry and, you know, whatever, as long as you follow through with that, then that's fine, right? So you don't get the marks completely, but you can get the follow through marks. So now, oops, I have a one-sided test. So my p-value, my one-sided p-value is somewhere between 0.15 and 0.20. Remembering again that you have to read these from right to left. Unless you love inequalities for some reason. But I don't, right? I don't want to think about which gator eats the larger value or whatever. I have a hard time with that. So, right, the alligator eats the big one. But am I the alligator? Or am I? Anyways, I always found it confusing. So I just use less thans across the board and make adjustments. Okay. So our p-value is somewhere between 0.15 and 0.20, right? That's all above 0.05. In fact, what could we have done? We could have said, well, if I force the area in the tail to be 0.05, right, the alpha level, then my t would have to be larger than 1.761. You're allowed to do that, but might be confusing, so I'm not going to do that with you. But if that makes more sense to you, then sure, on the test, you're welcome to do that, right? Okay. Step 4 is your conclusion. Now that you have your p-value on the test, and I think I mentioned this before, but it's worth mentioning again. If you've completely drawn a blank on how to find the p-value, what do I want you to do? I want you to just give me a reasonable range for the p-value, right? Just tell me, okay, it's between 0.05 and 0.025, for example. Sure, right? That's wrong, probably, unless you really hit the jackpot, right? Worth a shot. But as long as you follow through with that in your conclusion, then I'm happy, right? That's the most important part. Little typos, that's fine. Well, it's not fine, but it's okay. And so what do? Same format as before. We compare our p-value to our alpha level. If it's less than the alpha level, we have enough evidence to reject H0. And then what does that mean in terms of the question? So here, since our one-sided p-value is between 0.15 and 0.20, it is not less than the alpha level of 0.05. It is not less than alpha equal to 0.05, which means we do not have enough evidence to reject H0, which means we do not have enough evidence to reject H0. Usually that's not great. In this case, that's a good thing, right? What does that mean? Let's scroll all the way back up. Whoa. I'll snag this. Copy. Paste. Right. Here, just to recall that H0 is mu is equal to 5, and HA is that mu is less than 5. We're saying, okay, anything below 5 puts aquatic life at risk. And so is there evidence that the aquatic life is at risk? No, there isn't. That's a good thing, right? So there are cases where we're kind of rooting for for H naught. Usually we're rooting for HA, right? That's the go-getter. But in this case, therefore, there is not evidence that the aquatic life is at risk. And that's a good thing. Eee, smiley face. You could have also, if you prefer, you could say there is, sorry, the dissolved oxygen level is not significantly less than 5. That's the same thing. Okay, but here I use this one because it just takes the question and rewords it as an answer, and that's all I'm expecting. Or you can say, okay, then it's not less than 5. It's not significantly different from 5. And I can tell that I'm out of time, but what I want you to do is, this is a confidence interval. Oops. And so I want you to do this one on your own, right? Calculate the interval and interpret, and then we'll use that for review on Thursday. And that's good. With that, I release you. With that, I'll end this. You bet. Let me just
looking for the answer.